who will speak about very interesting things, how to park a car.
Thank you. Today I'll talk about parking function, bijection, and area statistic. So some content here were discussed in Peter seminar last semester, but that's just for the introduction part. So first, let me introduce what is parking function. So because now we are in Hill Center, so I'll use Hill Center as example. So here's Hill Center. Here's a free Python node. We know this is a two-way load, but we can assume in a parallel universe it's a one-way load for east to west. And there are some premium parking space on the right side of the load, so it's like this. So it's from number 1 up to number n. So because there are premium parking space, so the number of premium parking limits is limited, it's only n. So we assume that one day all the n cars we have the parking permits come to park one by one. So every car has its favorite parking space. So we use for each car I, we use PI to denote its favorite parking space. So now what we get is a sequence or a vector. It will be P1, P2, up to Pn. So what if a car's favorite parking space is already occupied? In that case, the car will park in the next available parking space. So we call this sequence a parking function if all cars can park. So let me give you an example. So for simplicity, let's say n equals to 9. Because if it's more than 10, then if I write numbers together, it will be misleading sometimes. So for example, I just write a random parking function. Maybe 2, 1. So is this a parking function? So in this case, first car will park at 8. The second car also produces 8, but it's occupied, so it will park at 9. And the third car will park at 7. But when the fourth car goes to 7, it's occupied, and there's no available parking space after 7. So this is not a parking function. So how can we make it a parking function? For example, if we say if this is 1, well, it can be so if it's a 1, then the car 4 will pass at 1. Then car 5 prefers 5. Car 6 prefers 4. And 7 prefers 2. 8 prefers 6. And then the last car prefers parking space 1, but it's occupied, so it will park at 3. So it means this is a parking function because all cars can park in this case. So now let's give a formal definition for parking function. A vector of positive integers P1 up to Pn. Each Pi is between 1 and n. It's a parking function. If is non-decreasing sorted version. we write like this with a bracket. Satisfies the other is an I for any I from 1 to n. So they are, of course, they are equivalent because if a car can park, so let's see, if this is not true, it means that then J, that Pj is greater than J. So if not true, Pj greater than J, then of course because it's sorted, it means Pj up to Pn totally n minus j plus 1 cars must park after j, but there are only n minus j space. So it means if this is not true, then it's impossible to park all the cars. And so in what case it's not a parking function? Usually, so in all cases, if it's not a parking function, it means too many cars prefer some large number parking space. So it's easy to prove both directions. So now that's a very natural question. So how many parking functions are there for any n? So we'll prove number of parking function of length n equals to n plus 1 to n minus 1. So there are many proofs for this one. I'll give.
And you have to say who were the first people to find this.
Oh, actually, I forgot who is the first people. Yeah. There are many proofs. I'll just give one example. So we can arrange parking space like this from 1 to n plus 1. And there are still n cars. So every car still has a favorite parking space. They can have n plus 1 as their favorite parking space. So actually this is just a map from n to n plus 1. So how many mappings are there? So there are n plus 1 to the n mappings. And because there are n plus 1 space, so it means every car can park, of course. Because when a car reaches n plus 1, if it's occupied, it can move forward. It can park at 1 if it's empty. So of course all cars can park, and there must be one empty parking space. So if we already have this parking function, and the empty space is Q, then for any j from 1 to n, from 0 to n actually, so this new parking function, P1 plus j, P2 plus j, up to Pn plus j, has empty space Q plus j, and everything in this line is mod n plus 1. So for a parking function, the empty space must be n plus 1, because if n plus 1 is a parking function, it means every car at most stops at n. So and for this kind of parking functions, in every n plus 1 such parking functions, it means there must be one of them which is a parking function. So the number of parking functions is just the number of such mappings divided by n plus 1. So it's n plus 1 to the n minus 1. So now we have some generalization for parking functions.
Yeah. Is there a nice bijection to label trees?
Yes, I will talk about that.
Great.
Yeah. So, first one, we can call it a parking function. This is a parking function such that they are sorted version. Satisfies pi greater than 1 less than a plus I minus 1. So the classical parking function I just mentioned is just one parking function here. So because if a is 1, then pi less than I. And then we can see that k parking function. So for this case, the non-decreasing sorted version satisfies pi less than ki. And here the number is k to the n times n plus 1 to n minus 1. Because for each k parking function, it can be written as k times q1 up to qn, which is one parking function here. So it's just the classic parking function I mentioned, and then minus a sequence. For this sequence, each Ri is from 0 to k minus 1. So there are kn choice here, and here there are n plus 1 to n minus 1 choice. And the third one, we can see it as x parking function. So in this case, x can be a vector. So it's a more general version. If x is such a vector, it means pi is less than a plus I minus 1 times b. So the number will be a times a plus mb to n minus 1. So now we'll mainly focus on a parking function. Let C and A be the number of non-decreasing a parking function of length, and let P and A be number of a parking function of length n. So we consider C and A first. For non-decreasing parking function, it will look like this. There are several ones. At least they should be, let me see. Yeah, we can say 0, 1. It doesn't matter. So if there are so many ones, and then it's a k plus 1 up to a n. So if there are k ones here, so we can delete these k ones. So there can be a map, and for a k plus 1, it must be greater than 2, and it's less than a plus k. So we delete all the ones, and for the remaining terms, for each one we just consider it itself minus 1. So it will be a k plus 1 minus 1 up to an minus 1. Then ak plus 1 is greater than 1, this is then a plus k minus 1. So this is another class of a parking function. In this case, it belongs to so here n becomes n minus k, and a becomes a plus k minus 1, which you can see from here. So it means that the recurrence relation for C and A is equal to the summation from k from 0 to n, then C of n minus k, a plus k minus 1. So for P and A, it's very similar. For P and A, because it's not sorted, so we need to consider the positions of the k1s. So of course the probability is n choose k. So for P and A, it's from 0 to n, and then n choose k. So now let's prove P and A equals to A times n plus A to n minus 1. So if I do Google, how can I know this? At first I didn't know, so I used a method and then found a pattern. Then I guess this is true, and then I can prove by induction. So now let's check the initial condition first. When n equals to 1, if n equals to 1, here this is 1. And of course it must be 1, right? If n equals to 1, oh, this is A, sorry. If n equal to, let me see. Yeah, this is A. So if n equals to 1, it means there's only one term in the parking function, and it can be any number between 1 to n, to A. So the number, of course, is A. And if n is 0, then it must be an empty vector, so the number is 1. And if A is 0, but n greater than 1, it's impossible. So the number is 0. And then you can check all these three satisfies, I think. Yeah. And then by induction, it means we just need to prove this identity. So we just plug in the formula for P and A to see a recurrent relation. And then let's define a function. This function equals to, so we have a minus 1 here. So we have a minus 1 over x. So the power here will be n minus k. Then the rest is k, but we want to write k as n minus bracket n minus k bracket. So for the first two terms, we can combine them. Then it will be a minus 1 plus n over x times the summation. now it's easy to see what it is. So for this part, this summation is just 1 plus x to the n. And for the second part, this is just a derivative of 1 plus x to the n. So this is n times 1 plus x to n minus 1. Then let's plug in x. X equals to a plus n minus 1. So here the coefficient here is just 1.
Yukun, what were you trying to do here?
Oh, I want to prove the number for PNA is this number.
Bijection.
Yes. So if a equals to 1, it's another proof for this.
Is that the elegant proof that you mentioned here also work for A parking function?
This one?
Does this extend to the proof, the more general statement for A parking function?
Which one? You mean this
Yeah,
one?
this elegant commentator proof. Can you extend it to prove the more general statement about A?
I'm not sure. I don't think so, because for A parking function,
It's not natural.
there's no direct meaning for whether you can park or not.
Yeah.
So I don't think so. So now let's talk about labeled rooted trees. Forest. So we can see the forest with a component here. It's a number. And the loops are fixed. So the definition might be somewhat different. So we can say it's just 1 up to a are loops. And totally a plus n vertices. So there are n non-root vertices. So we call this number TNA, the number of above forests. So if we already have a forest, it will look like this. Maybe here is a plus 1. So I want to prove the number is the same with PNA. So we only need to prove they satisfy the same recurrent solution. So if n is 0, it means there's no non-root vertices. So there are only a isolated points. So in this case, it equals to 1. If n greater than 1, a is 0, then of course it's impossible, so it's 0. And if n is 1, and then it must be a, because you have a choice. So now let's consider the neighbor of 1. If there are k neighbors, then we can delete 1, and for each neighbor, we let them be the root. We let them be roots. So this means TNA equals to a summation k from 0 to n, t n minus k, k plus k minus 1. Because if we do so, then this k non-root vertices will become roots. So it means the number of non-root vertices will become n minus k. And originally there are a roots. Now we delete 1, but we have k more. So then the new number of roots will be a plus k minus 1. So because this satisfies the same recurrence relation, it means TNA also equals to PNA.
But don't you need to pick the labels? Don't you need normal coefficients? You know? Is it an analog of this?
Yeah. Yeah, of course.
With the labels?
Yeah. All that different if not. Yeah. So since they are equal, so there must be a bijection. There are quite many bijections for this, but I will just present one which I found or refound. So now, bijection between a parting function and therefore multi-forest. So it's best to be demonstrated with an example. So now let's start with this example. So I should say this is a two-parting function. Because if I don't say this, sometimes a function can be both one-parting function, two-parting function, or some other eight-parting function. So now, because 1 and 2 are roots, so now let's have a two-line notation like this, from 3 to 9. That's why I chose the length 7. And now let's consider the sorted version first. So I want to let 3 be, let 1 be 3's parent, let 1 be 4's parent, let 2 be 5's parent. So this is doable. So you can see the parent of 7 is 4, the parent of 8 is 5. But this is not the original parting function. So let's sort this one according to the second line. If two elements in second line are the same, then we always write the smaller one first. So 7 is before 9. Then we compare these two. The second line is the same, but the first line is not. So it's actually it's a permutation. So it means 3 goes to 7, 4 goes to 9, and finally 9 goes to 4. So let's do a permutation for this one. Because 3 goes to 7, so it becomes 7. 4 goes to 9, so it's 9. 7 goes to 5, so it's 5.